ऑल राइट एवरीवन। तो आज हम लोग पढ़ने वाले हैं टाइप 4 ऑफ कॉम्प्लेक्स एनालिसिस। कॉम्प्लेक्स एनालिसिस में टाइप 4 ऑफ इंटीग्रल। We will see in this lecture, we will see how to evaluate real integrals using complex analysis. Okay, let's do some recap. By far we have studied some approximately 3 types of integrals. First was the integral of this type trigonometric. The second was improper integral of this type is f of z dz, in which we have taken some examples like integration minus infinity to infinity x square plus a square x square plus b square and dx. Okay, in this type we have taken this example like this. In the third category we have seen that function f of x with having some factor of cosine and sine function. Then in that case we take the imaginary or real part of the function and convert it into the exponential function, and that's we integrate our complex function over this contour, and using single residual theorem and comparison we get our answer. So by far we have studied the 3 types of integral, and today we will be studying the fourth category of integral. uh, so as far as we have studied this integral over this longer arc is 0, so I would like to suggest you that never during examination, for the examination point of view, you are actually not in need to calculate the integral over this arc. In examination it is actually there is a theorem called Cauchy-Gauss theorem. Okay, this integral over the simply connected domain is 0. So by far we are just taking this that integral over this arc gamma r is 0. Okay, that will be an assumption. And we know that whenever we have function f pz and qz, where the degree difference is q minus p is greater than or equal to 2, then integral over that gamma r will always be 0. And you don't need to show this, just you have to write that integral over this gamma r is 0. Okay, so that was a thing. If you are willing to show that this in the examination, actually nobody is going to cut your marks. This is actually will be a much beneficial for you if you want to go in depth with the complex analysis. Okay, so in today's part we will be seeing the 4 type of complex integral, and that will be uh, when some kind of this minus infinity to infinity some f of z dz, when function f of z has a singularities on a real axis. Now just if we assume this of a function somehow like this, so first this sin x over x of dx. Now you can clearly this function has a singularity as z equal to 0. Then how we can encounter this? So, although it has a real pole, a real singularity, but while we will construct this as imaginary part of integration or contour integration e to the power iota z upon z of dz. Now here you can see the function has a singularity as z equal to 0. So how we will construct a contour, because contour is a region or subset considered of a line made in such a way that it will not pass the singularity. So in general we have seen the whenever there is a limit from minus infinity to infinity, we construct a semicircular contour. So in this case also we will construct a semicircular contour, but there will be some changes here. Around z equal to 0 we have a singularity, and just in order to avoid this singularity not coming on this contour, we will just pass about over this singularity. Just we know that this is minus r and r. Just consider this as a minus epsilon, and epsilon where epsilon tends to approximately 0. So we will just at the end of applying limit we will get our answer, that we will see. The thing is we want that this contour should not pass over this on the singularity. The singularity should not pass on the lie on the contour. So we have just taken a turn over here. Now the orientation in everywhere is counterclockwise. Here it is clockwise, so the value of integral will be here negative, and here it is counterclockwise. So we will see that how we will be going to evaluate the integral over here and here. So for such cases, like whenever we have singularities over here, let's take some example. That will be our first example only. That's 0 to infinity sine x over x of dx, and then how we will evaluate the such integrals. Now just consider a contour, semicircular contour in a complex plane, which can be written in such a way like this. So I'll explain slowly. We have a semicircular contour moving here from minus r to minus epsilon. Then there is a turn here to this epsilon, then again connecting to this uh, r. Let's name this part as a gamma and this part as a gamma, capital gamma r. So considering a contour over which we will evaluate our complex integral, let's we have a complex integral letter. F of z is this e to the power iota z upon z. Okay, so we will just calculate the contour integral over this f of z, and we can write it as integral minus r to minus epsilon of f of z dz plus integral over this small gamma r, gamma this f of z dz. Then we will move to the integral from epsilon to r this f of z dz. Then this last part is integral over this capital gamma r of f of z dz. So these parts are required. We have to calculate the integral of this part, and we will use this for our final answer. So this part we can easily calculate by using residue theorem. We can see that a function has a single pole at z equal to 0, so we can write as limit. This its value will be 2 pi I times residue at z equal to 0. So we will get 2 pi I limit z tends to 0 of z minus 0 t to the power iota z upon z. We will get here we will get 2 pi I. Okay, and now moving ahead to this capital gamma r. For capital gamma r, as we have seen now in this part, I am not going to evaluate the integral of this capital gamma r. You just have to do is z equal to capital R epsilon. Just consider the radius of this as capital R and this as a epsilon. So you can easily get capital R, you can say small r iota theta. Then we as we will just apply the limit r equal to infinity, you will get the integral over this as 0, and using Cauchy principal value here you will applying limit r comma epsilon comma r tends to this uh, epsilon tends to 0 and limit r tends to infinity. On here we will get easily this minus infinity to the infinity. Combining those two integrals with this one and this one, we will get our function f of z, that is e to the power iota z upon z of dz. Now the only part left is to calculate the integral of this new small r. So for that case we will as we have seen in the previous part, that to calculate the integral of this bigger r, we consider the absolute value, because that arc is in general very big and we cannot find the exact integral. So but here this arc is evaluable because of its size, as epsilon is infinitesimally small. So we can consider letter z equal to epsilon e to the power iota theta, and we have our integral gamma is e to the power iota z upon z dz. We can write it as this arc move from pi to the 0, so we can just take a limit as pi to the 0 e to the power iota, that is epsilon e to the power iota theta into epsilon iota e to the power iota theta d theta divided by epsilon e to this is epsilon e to the power iota theta. We will just cut this and we will get iota. In order to reverse this, we know that if this z1 to z2 of our limit is like this way, we can just reverse the limit by doing this. You know this property of definite integral, we can write it as 0 to pi minus this. Everything is cut. On applying the limit epsilon tends to 0, you will get this 1, as only left is d theta. You will get minus iota pi. So from this you can say that if our function is having infinitesimally a lot of singularities, if assuming this, it is z1, z1, z2, z3, z4, and this way, so you can write this as integral over this small r gamma, we can write is as minus pi I times residue at z equal to that zi. Okay, all right. This is a formula. If you don't want to calculate the integral over the arc, smaller arc, using this method, you can usually you can use this method, this direct formula, minus pi I times residue of this function at z equal to zi. Okay, so here let me show you how. It is minus pi I, the function it calculate at z equal to 0. So at z equal to 0, we have seen the residue is 1, so you will get 1. So this is minus pi I. Okay, the formula which is using is valid, so we will get contour integration f of z equals to minus infinity to infinity e to the power iota x upon x dx plus integral over this gamma plus integral over this gamma r of f of z dz, f of z dz. So this sorry, this will be 0, and this we got minus iota pi, and here this is uh, what is, just a second, we have got integral as a 2 pi I. This is 2 pi I. All right, so on applying this we will get I think there is some mistake yet, I need to find out that once we will do on for making this here, we will get 3 pi I equal to integration minus infinity to infinity e to the power iota x upon x of dx. Now on taking this imaginary part, we will get a sine x by x of integration minus infinity to infinity dx. It is 3 pi, but it should not be the answer. It should be this pi sometimes. I need to check where I have made mistake. This is like this. We have calculated the residue is 2 pi I. This uh, why this is causing some problem? Give me just a second. I am going to check it. All right, now I've got a mistake which I was doing. That was definitely a silly mistake. Look, the calculated this as a residue at z equal to 0, but the thing is that this point z equal to 0 does not lie inside our contour. So the residue at this point will be 0 actually. Since the Cauchy theorem is that if the singularity lies inside the contour, then only the this integral over this f of z dz will be 2 pi I times residue at z equal to zi, summation this. But the problem is this, the z equal to 0 does not lie inside our contour. So on doing this, we will get this as 0. So this capital integral is actually 0. I'm thankful. I'm sorry, I forgot this. I didn't pay the attention here. So here we will get as 0. So our integral, let me write it as the next page. So by far we have seen that let me write it once again, that the complex integral contour integral is f of z dz as is minus infinity to infinity e to the power iota x upon x of dx plus integration over this r small r gamma r f of z dz plus integration over this capital R f of z dz. Now we have seen that the integration over this capital R is 0, and in the integration over this smaller r is minus pi I, and we will get this as and we have seen this is 0. So 0 equal to this our required integral plus minus iota pi. So we will get integration minus infinity to infinity to the power iota x upon x of dx equal to pi I. Comparing the imaginary parts, you will get minus infinity to infinity sine x over x of dx equals to pi and integration 0 to pi of sine x by x of dx equals to pi over 2. Okay, there is actually a way to solve this problem. There are two actually ways. In general, what kind of contour I have made here is the just we have seen that as z equal to 0, z has a problem. So in order to avoid this problem that it will not pass over this contour, we will make a turn over hit at z equal to 0, so that no singularity lie inside it, so the contour integration over this function will be 0. However, we can do this also, just consider contour like this way also. The, in order to avoid this, we can just move it like this way also. Okay, so this time our singularity z equal to 0 lies inside this contour, and while evaluating this integral, there will be a role of residue theorem here. So I am going to give you this problem as a homework, that try to evaluate the integral or by considering this contour, and just comment me the answer what you are getting. So we have completed our course of complex analysis throughout our all the, I think, in 11 lecture. This was our 11th lecture. I have explained everything: the analytic function, the evaluation of real integrals using residue theorem, the and Cauchy-Riemann theorem, the Cauchy-Riemann equations, and Cauchy integral formula and evaluation and the application of theirs. So in next lecture, that will I will bringing is on the base of that will be on the questions of complex analysis and all the important questions. I have made a PDF, and that I will upload it to you. Okay, so stay updated. Thank you.